Hello everyone and welcome back to the Data Journey YouTube channel. Here in this video we are going to explore a bit about the DBScan algorithm. And here in this lecture I'm going to explain you a bit about the theory of DBScan, and then we'll use just a practical use case on how we can fit this algorithm in Python. First, I'm going to get out here of the notebook and go here a bit to a drawing board just to explain of how DBScan works. So let's imagine the following two-dimensional data. I'm going to add here, for example, two axes. There you go, 1, 2. And I'm going to name these axes as income and age. Okay, so income should be the x1 and age should be the x2. Imagine that these variables are standardized, okay, just out of simplicity. Now let's imagine that we have the following data points. I'm going to put them here. I'm also to color them here in red, and I'm going to color, I guess, these data points in this way. Let me replicate these data points and let me put two data points right here. Okay, so DBScan is a bit different from other clustering algorithms, particularly k-means, hierarchical, as they are more related with the idea of distance. In terms of DBScan, we work with densities, and DBScan has only two hyperparameters. Hyperparameters mean parameters that the model does not learn and that we as users need to give to the model. And these hyperparameters are the following. They are epsilon and they are mean samples. We explore what these two will be in a minute. We just put this in the right color. Okay, so imagine we have an epsilon of 1. An epsilon of 1 means that the radius that we are going to draw outside or circling each data point will be a radius of 1 unit. And here, out of simplification, we'll assume that the radius of 1 unit is the following. So this one that I'm doing right here, starting on this data point that I'm going to highlight. Okay, so as you can see, I've just drawn a radius around the data point, considering this is 1 unit. Okay, if you have a radius of 2, you would have a larger boundary, so something like this. And if I have a radius of 0.5, you would have a smaller boundary around the data point, like this one that I've just drawn here. Okay, I'm going to remove it and say that this epsilon is equal to, let me go here, this epsilon is equal to 1. Okay, so there you go. EPS equals to 1 from epsilon. Let's think through the DBScan algorithm. So the DBScan starts by drawing this boundary around each data point. And here we now must go for the mean samples hyperparameter. And let's assume that the mean samples hyperparameter is 5. And mean samples just gives us an idea of how to classify data points based on their radius. For example, if I go here and I count the number of points that are inside this radius, I'll check 1, 2, 3, 4, 5. I also consider the ones where the radius touches, 6. So as this data point contains 6 data points within the radius of its boundary, we consider it, I'm going to put it with this color, a core point. Okay, and I'm going to write this one here. So oops, let me go here and let's consider this one core point. Okay, and there you go. Now let's move for another data point. I'm going to position our radius on this one right here. So as you can see, I'm positioning ourselves on this one, on this next data point, because it's a data point that's within the boundary of my core point. And I'll count how many data points, excluding the data point, we have in the boundary. So we'll have 1, 2, 3, 4. So here we have less data points than the mean samples that we are considering, which are mean samples equals to 5. And epsilon will be equal to 1. As the data points in the boundary of this data point are less than the mean samples, we consider this one a satellite data point. Now, a satellite data point is a data point that has been called by a core point, as our data point was. It doesn't reach the number of elements that we need to consider it a core point. So I'm going to call it satellite point. Okay, there you go. But this data point loses a privilege considering the core point. and that privilege is to call other data points within its boundary. So only this data point has the privilege to call data points in the boundary. So imagine that we would have a new data point right here, okay, that was only touched by this data point. This data point couldn't be considered for calculations within this cluster because it's only sitting in the boundary of a satellite point, okay? So imagining that this data point is right here, this data point is still something that we would need to assign later, okay? We can't go there because the satellite data point is the only one that is calling it. If I move the boundary here, we would see that this one is also a satellite data point. This one is a core data point, so I'm going to fill it in green. This one also seems a core data point. So just by recapping, what we are doing is moving the boundary and have the data point in the center, and then just counting how many examples we have inside the boundary. So here I'll go for a core data point as well. This one will now be a satellite data point, and this one and this one has 1, 2, 3, 4, 5. We can consider 5, so it's going to be a core data point as well. And let me just put this axis here. And now let's move the boundary for this one, okay? And now an interesting thing, this data point wasn't called by any core point, it doesn't contain any core point on the boundary, and doesn't reach the mean samples. So this is a new point that we are going to call the outlier, okay? So this is a novelty in terms of clustering regarding DBScan, is that it can consider outliers. Now pause the video for a couple of minutes and see if you can understand how you would classify these data points and these data points right here. Then return to the video and see if you could guess it correctly. Okay, I'm going to move the boundary here. These ones are outliers as well, so they get this color. This one will be an outlier as well because we don't have the minimum samples available in the boundary. And then we're going here, will be an outlier as well because these data points will never be a core point because they don't have 5 examples around them. They only have 4 because these are 5 data points. Now that's something interesting as well. Let me put here, this one right here. Now if we had another data point, for example a data point right here, then we would be able to form a new cluster here. But in this way we can't. We have our clustering solution. What we now have is that with this DBScan application, this one or these data points are what we consider cluster 1, okay? And unfortunately, all these data points will be considered outliers. So this is one of the setbacks of DBScan algorithm, is that it's really sensitive to epsilon and mean samples. Roughly, you would define mean samples as 2 times the dimensionality of your data, and you can try to find epsilon using some heuristics as well, although we'll not go too deep into it right now. But the interesting part is that you now understand how DBScan works. So we have core point, satellite point, outliers. Now let's go back to Python and see if we can fit a DBScan solution using scikit-learn. So I'm basing the notebook that we will do on my Medium article Unsupervised Learning series exploring DBScan. So I'll link it also in the notebook and in the resources of the video or description of the video. We are going to use a clustering algorithm on the taxi data here available at Kaggle, the New York City taxi trip duration. Although we'll not do a supervised learning as it is intended with this data, we are just going to use the pickups of the taxis to understand if we had to set up taxi stations somewhere for our cars to sleep, where would we put those cars? Now that would be something very interesting to do with this algorithm. So I have a file that's a sample of all the taxi trips that we have right here, because otherwise it would take some time to run the DBScan algorithm. I'll leave this sample in the description so that you can also work with the same file. So as you can see, in my folder I have this taxi data sample, which is a CSV file that I'm going to load to my Colab notebook. So I'm going to my Colab notebook, click this one, and now I'm going here to file upload, as you can see here. navigate to my folder where I have this taxi data sample, and I'm going to load it into my Google Colab. This should take a bit, but after a while our file will be available and we can start to code. Okay, so after you wait a bit for the file to load, you'll have it available here as taxidatasample.csv. So let's start by loading this file into our notebook, and I'm going to call it taxidata with pd.read.csv. And here what you can do, if you are not able to find where you've loaded the file, is go to the taxidatasample.csv, copy path and add it here. And here, of course, as I'm using the alias pd, I'll need to do import pandas as pd because I'm using an alias, so I need to use the alias of the library. Let's run this one, and now checking the add of our data. Very cool. So we have basically information about some taxi trips. We have a vendor ID, but we have the pickup date time and the drop-off date time, the number of passengers, the longitude and latitude of the pickup and of the drop-off, and some other information about the taxi trip. Now, in Kaggle, the original objective of this data is to predict the trip duration based on certain information. Now here I like to give it a twist and use this to do here a toy business problem, which is based on the location of the pickups, mainly where people were picked up by a taxi. If we needed to set up a certain number of stations for taxis to go to these places quicker, so places where we needed to have taxis available, where should we put our taxi stations? And this would be an unsupervised problem. And here we also had it a twist because we want at least each station to serve at least 100 trips. And this is where we'll actually use the min samples parameter. Okay, cool. So let's continue here with our examples. I already know that there's some errors in the longitude of the data, so I'm going to remove them. So here, filter errors in longitude, because these are like trips that were taken from California to New York. I find it probably a bit odd and impossible that someone picked the cab in California and was dropped off in New York, but who knows. So here taxi data is equal to taxi data.log, and here I'm going to filter out the longitude, where this pickup longitude is basically larger than minus 100. Okay, so there we go. Now we have the taxi data filtered. Now next step, to avoid doing a huge parallel here on the notebook, I'm going to pick up some code here from the article, the Medium article, and I'm going to pick up some code here, and I only need these two for now because this one is already solved in the Google Colab. And I'm going to go here, and I also need to install here as I'm doing. The article will be corrected with these installs and you check it later, and also the notebook will be much more organized with these installs on top. Okay, just as I'm coding at the same time here, it's good to have this one on a first pass. So I'm in here, and I also need contextually. Okay, I think it's correct. Let me see, contextually, exactly. So let's just run these 3 installs. Okay, let's wait for this to finish. Probably, as I was already doing some tests with this, I'll have requirement already satisfied. If you don't, this is the first time you are installing this in this Colab version, in your Colab runtime, then you'll see something different. Okay, but let me open now a new code, and I'll pick up here, pick up just this code. Again, the imports are here, but they will go on top when the notebook is organized. And let's just visualize New York map. This will let us view all the pickups that we have in the city. Now, as you can see, we have these data points with the pickups on New York City. And now what we would like to do is to run a DBScan solution to see where we should put our stations with at least 100 trips. Of course, we would like also to use the epsilon parameter to see what is the impact of us setting up those stations. First, I would like to scale this data, so I'll do scale taxi, and I'll need to import from sklearn.preprocessing import standard scaler. Whoops, there you go. So standard scaler dot fit transform of my data. Okay, so I'll go here to taxi data. Let's go see it here, and let me go down taxi data, and I'll use only pickup longitude and pickup latitude, because these are the two variables that I'll use for my clustering. I'm also overflowing a bit, and I have a bit of OCD with this overflowing of the 79 characters rule, so let's do it in this way. Let's see if everything is correct. It is. So now we have our data scaled with z-scores as well, so it normalized the variables. And now, of course, for what we want to do, from sklearn.cluster, let's import DBScan. Okay, this is the algorithm that we will use, of course. Now, for DBScan, this is a typical scikit-learn fit process, and I'm going to first define the DBScan. So DBScan algo will be a DBScan with the following: EPS equals to 0.25, this is the epsilon that I'm defining, and mean samples will be equal to 100. Okay, cool. So this is my algorithm. I can run and prepare the object, and now what we will do is the fitting of the clustering. And here I'm going to do, on the taxi data, I'm going to do DBScan cluster of DBScan algo dot fit predict on where? On our scale data, of course. So this scale taxi that we have right here, and this is where we are going to fit our algorithm. I'm just going to write the result of the fit predict to the original data, taxi data, because it makes sense, as we'll want to plot the original longitude and latitude from that data. So let's run this one. This should take a bit, but should not take too long. Okay, very cool. So let me go here to the taxi data. Now for the different trips, we would know to what station we should assign them. These first ones are all assigned to station 0. Okay, so now we have the size of our clusters. We have how many examples are allocated to each cluster. If you see here, we have for cluster 0 around 94,000 examples. For cluster 2, 2,219. And can you guess what this -1 is? Pause the video for a minute and see if you can understand why we have this -1. So this -1 is exactly the outliers. We have around 881 outliers in our dataset that weren't allocated to any cluster. And that means these data points that don't match the criteria of mean samples. And that's why they are allocated with -1. So of course, it makes sense for us to remove these outliers now that we want to plot the clustering solution. So that's what I'm going to do here. So taxi data should be equal to taxi data.log. Taxi data dbscan underscore cluster is different than -1. You can do this in several ways. You can do this using the indexes, however you want it, as long as you remove these data points from the taxi data. Okay, so if you are having any trouble understanding these types of instructions, you can also check my Python course in the description of the video. So you'll have a link for the Python for Absolute Beginners course on Udemy. And if you want to start to work with Python a bit better, you can go to my course and just study the fundamentals on how Python works. Although in that course I don't go deep into data science, I really teach you the basics and foundations of Python. So if you are curious and you like the way that I teach, you can go there and enroll in the course. Make sure that you find a good Udemy promotion time to grab it, because Udemy is always running promotions as well. And also in the description, you'll have links for the articles that are the base of this video, so you can see them for free. Just tap the links and you'll be able to access the articles. Okay, so now let's do the following. Let's calculate the centroids of each cluster. If I have here, for example, in the taxi data, if I have here an example of what's the cluster of each taxi trip, right? I can now calculate the centroids, and I'll calculate them by seeing the average of every data point that is in the cluster, right? If I go here, so the average of this cluster would be a data point here in the middle, because it's the average of the values. Of course, the outliers doesn't make sense to plot their centroid, because they are scattered throughout the space, throughout the dimensional space. So if we calculate the average of the outliers, we would get a very, very random point, because imagine that these outliers were here, for example, the centroid of the outliers would be inside this cluster as well. So it doesn't make sense to have outliers with centroids, okay? Those two concepts don't match each other. So now let me calculate the centroids, and I can do that very quickly with the group by command. So I'll go here and I'll do centroids dbscan should be equal to taxi data dot group by, and here I'll group by what? The cluster DBScan variable, of course, so this one, or DBScan cluster variable, and I'll use the pickup. I need to check the average of two columns, the pickup latitude and the pickup longitude, which are the features that I've used in my cluster. Okay, so this one, and use a latitude. Then of course don't forget the mean method to extract the average. So here I'm grouping by the DBScan cluster, and then I'm calculating the average of the longitude and latitude by these clusters. And here, let's run this one. Now we should have the average latitude and longitude of my clusters. So there you go. So I know that cluster 0 is on longitude of minus 73.98 and latitude 40.75 degrees. So very, very interesting. By using this solution, I know where I should have my taxi stations. That's the very interesting part of this solution, because now I have a cluster that was done based on all the examples, on all the taxi trips that I have, on all the data on the taxi trips. I've used the DBScan cluster to make sure that all the stations that I've set up have at least 100 trips by the mean samples criteria, and now I can see where is the average of these clusters, where I'm going to set up, and I'm assuming I'm setting up the station at the center of all those trips occur. Of course, we could have different criterias, but here that's the one that we'll follow. So now, just one last step before we go, which is plotting this data in a plot. And I can use exactly the same one that I have here. I'm going to even copy the code. Let's go here, and instead of using the original data and pick up the latitude and longitude of all the trips, I'm going just to use the centroids DBScan here in the scatters. Okay, the New York map is exactly the same. I'll keep it. I just want to see different data points in the map. Okay, very cool. Now we have here the 3 stations that we should build. So it makes a lot of sense, because if you see closely, you see that you should have a station in JFK Airport, another one in LaGuardia, and another one in the Upper Manhattan Island. So makes a lot of sense, because these are hot spots for taxi pickups. So it's very, very interesting that we could apply this solution. Now, if you return to the map and we go here, you notice that there are a few trips that are outside of this area, and they are considered outliers. So they'll never have a taxi station assigned to it, because they don't match that criteria. Because these areas, in the context of DBScan, have low density in terms of data points, so they don't really form a cluster. And it's interesting to have this concept of density with a map, because it's kind of intuitive, but this concept of density can be applied to any type of data. Okay, here doesn't need to be in a map, but here using an example where you geographically plot data helps a lot understanding this algorithm. Before we move, just a couple of info. So the DBScan algorithm, and I think I didn't tell you this, is that it finishes when all the data points have been characterized with at least one of these in at least one of these groups: core point, satellite point, or outliers. So do a pass through all data points, classify them, and after we classify all data points, the DBScan algorithm will finish. Just to recap, let me go here to my notebook, and as you remember, so to fit a DBScan solution in Sklearn, you just go for the DBScan function, you use the EPS and mean samples parameter, and then you fit that solution into your dataset. Be mindful that DBScan can be pretty intensive in terms of computation, and for certain systems may even blow up your computer, or at least it can have a lot of leakage. Be mindful that that might happen, at least when you are using Google Colab with limited resources. What I recommend right now is that you play around with these EPS and mean samples parameters, see how they change the solution that you have here at the end. Also in the Medium article, I show another example of another set of parameters and how they generate different clusters, or what types of additional clusters they will generate. Feel free to check the Medium article to know more. It's very good to show you this algorithm. I hope you enjoyed it and that you can use it in your projects when it makes sense. The weaknesses of DBScan is that when clusters have different density, for example, when you have data points in a cluster that are very spread apart, but they are still a cluster, and in the same data set you have data points that are very close together, DBScan has some difficulty understanding those clusters, because the EPS and mean samples parameter are common for the entire solution. So that's a drawback of DBScan. Pay attention to it when fitting the solution. As with most clustering algorithms, the secret lies in the interpretation of the clusters and understanding how you can apply them to your business or research problem. It's very interesting that you have that mindset when fitting these types of solutions. If you've enjoyed this video, feel free to message me on LinkedIn or write something in the comments. If you want to ask something, I'll be really happy to help you, and I'll see you in the next video.